So what I'm going to talk about for the next 25 minutes or so is I'm going to revisit something that I talked about last year in Portugal as part of my rather pretentious past, present, future trilogy of presentations. I talked about this, as I say, last year and got various bits and pieces of feedback from people, all of which was very useful. The most difficult thing that came out of that feedback is something that we already know is the most difficult thing about computer programming, which is naming things. We've been talking about token by token debugging, but these things aren't really tokens that we're talking about. I've talked about primitive tracing in the past, but that's not strictly correct either. We had a meeting in Dyalog a couple of weeks ago, and I asked people in the room what they figured might be a good name for this, and the best option that came up was bit-by-bit poking. So I like that one. I'm not sure that I'll be using that during this conversation, but you know, who knows, it might slip out. But whatever we call it, I'll demonstrate stuff to you now. Can I just ask how many of you in the room saw the presentation last year in Portugal? Okay, so a lot of what I'm going to show you now is not going to be a surprise to you, although I'll try and wrap it up in a surprising fashion. But hopefully those of you that haven't seen it will see the benefits of what we're going to talk about. First of all, though, an apology. I did this a year ago. It was some work that we'd been looking at. We got very excited about it. We wanted to talk about it very quickly. It was never intended to be in 19. I know a lot of you were keen to get it as soon as possible, but it will be in 20. It might not be exactly how you see it this morning, but this or something very much like this will be in version 20. And for many of you, it might just change your lives. We'll see. I said that last year and then took it all away from you again. So what am I talking about? I'm going to talk about a new level of tracing in Dyalog APL. Let's have a look. So I've got a workspace which has got a bunch of stuff in it. So traditionally in Dyalog APL, we can trace into a function. Okay, and APL has always been line-based, so we can execute a line of code. We could trace into our own functions that are defined in that line of code, but that's the level of resolution that we've got when we're tracing. And Control-Enter is the keystroke that we use to trace into an expression. Okay. What this new level of debugging does is it allows us to drill deeper into our APL code. So I've got a keystroke on my machine that's configured, which is Shift-Alt-Enter, which allows me to go into parts of a line. So here we've got a diamond. I hope the font's okay for everyone. Please shout out if it's not, and I can increase it. So here we can go into the diamondized expressions in this line of code. And if I hit Enter now, we move on to the next diamond and enter onto the third diamond. So we can now break our line into the individual diamondized expressions. As we wrote it, now we can debug it at that level. But cooler than that, if I type Control-Shift-Alt-Enter to go into this diamondized expression, I can hit Shift-Alt-Enter again to go into the primitives that are in this expression. Okay, so we're going to evaluate the iota. I hit Shift-Alt-Enter again, we're going to hit the assignment, we get into the +/, the assignment, we get into the tally and the division. So we can step through our primitives or our tokens or our bits. We can, for our arbitrarily complex lines of APL code. I'll make a point now that I was in the Tacit workshop yesterday. I have never seen such an average APL conference. Expressions to do averages and means have been everywhere the past 2 days. Morton, I think, used the mean train on at least 2 of his slides, and it was all over the Tacit thing yesterday. And here we've got a traditional APL diamondized expression to calculate a mean. But there's lots of ways we can write this. We've got this diamondized expression. Oh, and here's something that I can do now is the If I hit Control-Enter on this to just trace that, that does nothing. But with my new keystroke, I can just trace this directly from the session. It doesn't need to be in a function. I can take any expression on the session that I've input into the session and trace through that. We might have written our mean as a defun. Okay, I can trace into that, and we can step into the defun and see exactly what's going on. Okay, no surprises there. I might have written the mean as a train, and this is where this token by token slash primitive tracing slash bit by bit poking, I said I wouldn't say it, can't resist it, really comes into its own, because we can see we're going to call the mean. The first thing we do is call the function on the right, the tally. Second thing we do is call the function on the left. Third thing we do is call the function in the middle, and that's our expression. So what I've got now is a function that's got a bunch of tacit definitions of interesting things, and we're just going to build up on this idea of this token by token tracing to see what we can do. So here we've got a simple, let's not look at that one, let's just come down to the straightforward train definition. So we can step into what's going on in our expression. This is great, this is useful, this is interesting, but wouldn't it be nice if we could also see what our arguments were at each stage? So if we come to the session, and we go to Tools, Primitive Tracing, Horizontal. What we get now is we get a UI. I'll just resize this a little bit, where we can see, oh, now, is it the top button, Morton? How do I get that now magnified round?
You press the little button at the very top.
Yeah, I'm doing.
Oh, it only works with...
Okay, never mind, it doesn't work. I'll use this thing. So what we can see here, we've got a window that says what's the current function. The current function is iota, and we've got a little box on the right that shows us what our right argument is. We're doing iota 10, there's our 10, and there's no value in the left argument. But as I trace through this, we can see that, oh, hold on, wrong window. When we get into mean, we're about to execute the mean function. There's our argument. We're going to do the tally first on the iota 10, then we're going to do the plus reduction on the iota 10, then we're going to do the division of the 55 that came from one side of the expression and the 10 that came from the other. This is all cool. One of the other bits of feedback that I got from last year was that there's a lot of wasted space here. You know, when we're looking at the function here, this is all, let me put that somewhere where I'm not going to be tempted to click it. A lot of dead space here, so we sort of thought, okay, well, what might be cool would be to have an option to display this in a vertical layout so that there's less wasted space for displaying the function. So I put in some time saying, okay, well, let's configure different layers. We'll have a horizontal layout, we'll have a vertical layout, and that was very cool. And then I thought, it's all getting a little bit difficult. Why don't we just use the technology that we've currently got, which allows me to drag and drop things in, so I can basically say, you know what, I'll have my left argument. Oh, that's not gone quite very well. I'll have that somewhere else. In fact, why don't I just drop that down? Oh, hold on. Why don't I just drop that down into the bottom of the debugger? Wouldn't that be good if I could just do that? Okay, bear with me. Yeah. Why isn't that just working? I mean, you know, everything has been fine. Well, that's annoying.
PowerPoint running in the background somewhere?
Oh, no, I'll tell you what right, no. So I know exactly what this is. I've got this... and I didn't try this before. I've got this thing running which displays the keystrokes, and I suspect that's displaying an overlay on the screen. Well, that would be good, wouldn't it?
But you're very virtual.
Right. Okay. So let's just try that again. So you're not going to be able to see my keystrokes anymore, but hopefully I will manage to tell you. Right. So we can drop that there. We can drop that one there. We don't need this anymore. And now as we go through these expressions, everything's nicely embedded around the debugger that we're used to using. Okay, and of course what I can do is I can undock this. I know a lot of you don't like docking. I'd love to have a conversation with you about why you don't like it, because you know it does make a lot of this dynamic layout stuff a lot easier And, you know, we don't have to enforce anything on you. Maybe not now, but another time. Okay, but the point is, you know, once we've set this up like this, I can come out, I can save my session. Okay, I can come out of the interpreter. I can come in again. I can load my workspace. And then when I start back again, I'm exactly where I left it, with everything still docked in. Okay, so let's come back to one of these examples. Here is another use of mean. A lot of times it's useful. Yes, it's great that we can see the arguments. What would be nice as we go through this would be to be able to see the result of the previous thing that happened. So we've got a little bit more UI. We can display the previous. Okay, and what we get here is we get another bit of UI, and again we can pull these out and dock them anywhere. Where, in fact, let's not have that. Where the pane on the right is going to show us the previous function that we run, and the pane on the left is going to tell us what it returned. So we're going to go into this train. First thing we're going to do is the tally. We're going to do the tally of the 5x2 reshape that we see on the right-hand side. And now we've executed that. So our current execution has moved on to the sum, but up here, this is telling us that last thing you did, the tally, returned 5. So we've got both what we're about to do and what happened recently in the past. And of course, we can take this, and it might be useful for us to all right, bear with me. And we can stop that doing that, I think, and then we could, for example, just decide to drop that in there, and then as we go through, we've got all the information again around the debugger that we've got. But so that's kind of cool. Okay, we can of course minimize this if we're not particularly care about that at the moment. We can minimize that. That's a standard feature of our docking, and then as we go through, we're just getting all of the left and right arguments and so on. So one of the tricks with this, or one of the difficulties with this for us, was to get this highlighting correct when we're running a tacit definition, highlighting the right bit of text. And that's important when you're looking at the text here. But it might be nice to be able to view this function in a different way. So if I now come to the UI and do view function, then we get the window that we saw before that shows us the current function. I could now, for example, just choose to dock that there, which is nice. Again, everything's nicely contextualized in terms of the geography of the screen. But I've got an option here that says, show me this as a tree. Okay, so now as I'm going through my train, the function that I'm about to execute is both highlighted in the text so that I can see where it is in the code that I've written, but I can also have an additional representation of it up there, which is another very useful way of looking at your function. And we can extend that to use the other boxing forms. There's, I think, there's a minus trains equals box form in square bracket box, and we can, you know, open up the various display forms that can be used here as well. Okay, right, so let me just got a piece of paper here with scribbled notes, and I've talked about quite a lot of this. Oh, right, so now would be a good time just for me to say this is all the window with the Windows IDE, okay, which is where I spend most of my time working. But of course, a lot of you might be on other operating systems and might be using RIDE. Okay, we've not forgotten you there. Here is a RIDE session running on my MacBook. Okay, and here we can do exactly the same sorts of things. Let's not do that one, it's not particularly interesting. But here we can go through the mean train, and we get the same interface in RIDE, which is very useful. Okay, so we're not just talking about Windows IDE stuff. This is coming to RIDE as well in the fullness of time. I'd probably rather come to the questions later, Kai. But don't forget, We can come back to the slides or whatever to contextualize it when we do that. Okay, so yeah, so we got it in right as well. And I probably shouldn't say this, but those of you that use a TTY interface, work has been done to make it work there. But only because it was just cool for me to do it, not because I necessarily want to encourage anyone to carry on using the TTY version. Okay, so that's all of that. I mean, and the rest of this is basically just going through, you know, all different tacit definitions of things. I mean, here, for example, this is a train. Okay, a train is 3 functions joined to each other. In this case, the function on the right is mean, that we've done to death now. The function on the left is this concatenate with axis. Now, here's a thing that I should point out, is that I said one of the most difficult challenges we had was to get the highlighting correct here, and in this instance, it's incorrect. Fortunately, we've got this view here that tells us that actually the function we're about to execute does include the down arrow character, and this isn't correct yet. So, you know, displaying it this way is great for you as users, in case if we've got something wrong, you've got another way of looking at it. But it's also great for us because we can look at it and think, well, that's not right. We should probably fix that. So, yeah. So we've done the mean. We're now going to do we're going to concatenate the down arrow on the end of our result. So that's the result of that expression. Oh, we haven't done it yet. That's the result of that expression, which has now got all the down arrows on the bottom. And then we join the two things together so that our result just has all the mean values at the bottom of the original data as well. But then that brings me to something else which is kind of cool. Oh no, I'll come to the kind of cool thing in a moment. So I was also in the tacit workshop yesterday. I mean, this isn't intended to be me teaching you how trains and tops work, but it's me showing that you don't necessarily need to spend a lot of time really understanding how they work, because you can just trace them and look at them and learn by interacting with things in the debugger. So here's one of the examples that came from the tacit workshop yesterday. It's a case-independent match. So what this does is it first of all calls quad C on the right argument, uppercase hello. Then it calls quad C on the left-hand argument, the lowercase hello. And then it calls match on the result of both of those, which have now both been lowercased. And we get our result. And then we can just go through all sorts of arbitrary expressions and see exactly how things are going on. Oh, and no, here's a good example. This was another one that came out of the thing yesterday. This line and the line underneath it are pretty much doing exactly the same thing. They are both calling intersection, they're both calling unique, and they're both calling without. Okay, but one's got a lot of extra stuff around it. The train version just calls intersection, just calls unique, just calls without. But it just doesn't have any additional noise around the bit of code that's actually doing the work. And once you can recognize those things, and once we give you the tools that allow you to dig into those to check that your understanding is correct, if nothing else, or at least learn by going through, you know, it's a richer, easier, not only development experience, but those of you that are educators, you know, you're I think going to find this very useful in terms of teaching people what's going on. I did feel a little bit guilty yesterday in the tacit workshop, sitting there at the back, knowing that I had, in fact, using this to solve a lot of those problems, knowing that the rest of you didn't have it, and I was going to show it to you the next day. So, you know, sorry about that. There's another thing, there's some more interesting things. Here, for example, this expression here is an idiom. It does, what does it do? It does leading space removal. This is an idiom in Dyalog API, which means the interpreter has special cased it and runs it as a single operation. So by default, we can't trace into that. I'm hitting the token by token tracing keystroke, okay? And it's just, hold on. What's going on? It's just treating it as a single entity. But if I go to one of my options, which is trace idioms, then we can go into, what's going on? We can go, oh, I've done something strange. Let's switch that guy off. Okay. Now we can trace into our idiom to see how our idiom works. And there's a question about which of those settings is best by default. Do you want to know it's an idiom and know that it's a single entity, or do you want to trace into it? But at least with the UI as it is at the moment, you have the option. Now, there's a couple of other things that were in those options that may or may not make it into 20, but there were things that came up from ideas with colleagues, and I thought, well, let's see if we can make that work. One of them was the idea of, you probably can't read the menu, but there's one here that says show history. Okay, and what show history says is when we go through a line of code, was it not? Yeah, right. So when we actually get to running the functions, you can hopefully see there's a yellow highlight of the bits of the code that we've already hit. So we can see as we're going through this complex train, we're evaluating all the functions essentially right to left, but in threes, and we get this extra highlight as we hit each of those bits and pieces. It may be a useful way of following which bits of your train have already been executed. You know, so we can do that. That may be a useful thing. It doesn't work perfectly well at the moment. And if we don't think it's worth putting the effort in to make it work perfectly well, we'll just quietly take it out. Okay, but if it is useful, then, you know, we can fix it. We can fix it and make things work. One of the other things that when we go through this stuff, we might get to a function. Let's say, for example, this catenate. Let's switch the history off. Okay, we might look at this and think, well, this is great. I've got a left argument and I've got a right argument, but where did they come from? You know, where did those come from? So here's an idea that I had. I added a where did this come from menu item. Okay. So we'll switch that on. We'll go back through this train. Now this is very experimental, and this works for about 20% of this line of code. Okay, but again, if it's a useful thing, we can put the effort in and maybe make it work in more of the cases. But let's trace through this. So we're going to call the iota. We're going to call the iota on. We see we've got the iota. We're going to call iota 100. And then what we're going to do now is we're going to call row. Okay, but the window that's showing us the right argument tells us that that's the right argument, but it's come because it was the return value of iota. Okay. So we can keep going, and then we can see the reshape. The row returned a matrix. Now we're going to go into our train. Now at this point, we've lost the information about where these bits and pieces have come from. But as I go through here, okay, we get to this point. We're about to do the division, and it tells us that what we're dividing on the left, well, that came from the sum, the plus slash, and what came from the right came from the match. Tally, forgive me. So it may be useful that if we can display all of this information, then we don't need what did the previous function return, because again, including it in these windows, in the left argument and the right argument windows, it gives you much more context. We're calling this with this as the argument, and that came from that bit of the expression. And that might be another rich way of learning how the various parts of your APL expression interact and glue together, and how things happen in the order that they happen. Right, so what else have I got on my piece of paper? What other sneaky little options have I got that yeah, not much really. There's a couple of other things that might be interesting. If I pull that out. Oh, hold on. I wish I hadn't done that. Where's that gone? Right, yeah, so this is one of the problems with docking, of course. So I mean, it's good that I've hit that. Let me see if I can come back to the session. Okay, let's just do options. No, let's do this. Hold on, let's just view function. No, it's gone, isn't it? Oh, there's current function. Right, okay, so one of the things here, let's do this, is there's an option here that just says save as tip layout. So I'm just going to click that now, and then I'm going to close this, and then I'm going to come back to the debugger. Okay, and we'll just trace into this again. So what we've done is we created a layout. It was a very simple layout, but we saved it as our tip layout, which means that when we hover over the highlighted function in the middle, we can get whatever we defined as our, this is how I want my tips to look, we can have that there. So you can have your left and your right arguments always visible, and if you want to look at the tree, then we can just pop that up as you hover the mouse over. That might be a useful thing. Something else which I've got, which I actually clicked by accident earlier, was minimize when empty. So for example, as we go through this, if the left argument has no value, then we'll just minimize that to the left. Okay, one of the problems with that, of course, is that everything's moving around all the time. But if maybe the left argument was at the bottom, okay, then it's less of a distraction if it keeps popping up and down. I don't know, but it's there. We may take it out, we may leave it in. Feedback is important. And, you know, and all of this stuff takes time to do. And if we do it and nobody likes it, then it was wasted time, or at least time we could have spent better doing something else. Basically, that's it. It's that deeper level of debugging, so you can trace into your expressions, understand or teach how the trains work, keep track of your arguments, where they came from, what they are. And hopefully, I don't want to say it'll encourage you to use tacit programming more, but it might make you more comfortable to, in the first instance, read other people's tacit definitions. And then from that, you'll learn to recognize them, and then hopefully, or if you want to, feel more comfortable writing your own. Thank you.